Okay, hi AP Physics. This is the first of a few short videos about RC circuits. You can see that I've already drawn an example of an RC circuit up on the screen. An RC circuit basically is a circuit that has both a resistor R and a capacitor C. And the main thing you need to know about these circuits is that their behavior changes over time. Up until now, all the circuits we've talked about, basically they're either on or off, and they transition between being on and being off basically like instantly. But RC circuits take a little bit of time to charge up when you first turn them on, and then to discharge when you turn them off. So, in the example that I have drawn, suppose that I take the switch, which is this part here. Suppose I take that switch and I move it over to the left-hand side so that the resistor and the capacitor are connected to the battery. As soon as I make that connection, current will begin flowing clockwise through the loop, like that. And as that current flows, it's going to begin depositing charge on the capacitor. So, in the very beginning, when the capacitor is empty, it's going to be relatively easy to push current into it, and I'll develop a little bit of positive charge on that upper plate. I'll develop a little bit of negative charge on the lower plate. But over time, as more and more charge accumulates on the plates, it's going to require more and more effort, or more and more work, more energy, to add additional charge to those plates. So at the very beginning, it's pretty easy for current to flow, and so the amount of charge on the plates will increase fast. But it gets harder and harder, which means that the amount of current flowing is going to get gradually weaker, and eventually the EMF provided by the battery won't be enough to push any more current, which means the current is going to stop. And that's even if the switch remains in that left position, so that it's still connected to the battery. So let me take my little pluses and minuses away. So let me start by jotting that down. So initially, current flows easily. And it actually flows so easily that in that initial instant, you can basically just pretend that the capacitor's not even there. You can treat it like a wire. So if you wanted to know what the initial current would be, if we just pretend the capacitor is a wire, I would say that the current should be E divided by R. And that would be it. Now, after a long time, or in the final state, I'll put eventually. Eventually, the current stops. And when the current stops, you can sort of informally describe the capacitor as being full. Now, of course, full depends on both the capacitance of the capacitor and also on the EMF of the battery that's powering it. So full is kind of a squishy term. It depends on what the capacitor is connected to. But when it becomes full, the current stops, in which case you can basically think of the capacitor as being a break in the circuit, as if the two wires are disconnected from each other. And it kind of makes sense, because in a capacitor they literally are not electrically connected. There's a gap between them filled with either air or a dielectric of some sort, but it's not a conducting pathway. It's just that it takes a little bit of time for the fact that they're not connected to really matter. So again, we start out easy flow of current, and then the current gradually gets weaker and stops. So that's for the charging process when I have the switch on the left. So let me label that as charging. And while that's going on, the potential difference of the capacitor is going to be increasing. You may remember our main capacitor equation is Q equals C delta V. So the potential difference, delta V, for the capacitor gets larger and larger in magnitude as Q accumulates. Okay, so let's talk about discharging. To discharge this particular circuit, I would move the switch to the right position. The way I have the circuit drawn by default, the switch is sort of like in between, so it's not touching either the battery side or the plain wire side. So I would describe the capacitor as being isolated in that case. But if I want to discharge it, I would need to move the switch over to the right. So if I throw the switch over there, as soon as I do that, the charges that are built up on the plates, let me draw in my pluses and minuses again. Those pluses and minuses now have an escape route. When they were connected to the battery, the EMF of the battery was preventing them from flowing back or equalizing. But if the switch is over on the right side, those positive charges can move along. Whoops. They can move along this path and eventually make it the whole way back to the other side of the capacitor, where they can neutralize with the minus. I think to undo that, I have to step it back. So, when I put the switch to the right, that's going to start happening. And at the beginning, I should start with the word initially again. At the beginning, the current is going to be strong. And the reason it's going to be strong at the beginning is that the capacitor plates have a lot of charge on them. Since those charges repel from each other, there's going to be a lot of force exerted on those charges. They're going to accelerate away from the capacitor quickly, and that means you're going to have a lot of current. But as the plates empty, the force that those charges exert on each other gets weaker and weaker, and that means that the current also is going to get weaker and weaker. So just as with the charging case, I know that eventually, again, the current is going to stop. It'll get weaker and weaker, and eventually it's going to stop completely once the capacitor plates are empty, once the charges have equalized. So the basic idea, if I were going to sketch this as a graph, I'm going to make a graph of Q. When I'm charging the capacitor, I know that it starts at Q equals 0, and over time, Q is going to increase, but it's going to level off to some maximum value. And I'll show in the next video that this function involves an exponential. There's like an e to the x in there. But qualitatively, what you need to know is that it starts out changing rapidly, gradually levels off at some maximum value, so there's an asymptote there. And similarly, if I were to graph Q for the discharge, it starts at some initial value, and then it decreases, asymptoting towards 0. So again, the change in Q is rapid at the beginning, and it gets gradually more and more gradual. And so this function also is exponential. What else did I want to say in this one? So I'll talk about the forms of those functions. Why don't I go ahead and do that now? So this is still for the simplest case, where there's just like the one resistor and the one capacitor. But the growth function is going to look something like Q max times 1 minus e to the negative t over RC. That is not a very pretty RC. So the growth function has a form like that. And the decay function is simpler. I'm going to use a Q naught this time instead of a Q max. But it would be Q naught times E to the negative T over RC. If I were interested in a different quantity instead of just the charge Q that's on the capacitor, it's going to be similar. So for example, if I wanted to know about delta V, as I wrote over on the left, delta V is Q over C. So if I were going to graph the potential difference of the capacitor, it's going to look qualitatively the same. I'd have to change the axis labels, but it's going to look basically the same. I'll just have a different coefficient. Like instead of Q max, it would be delta V max, or Q max over C would be the same thing. If I'm interested in the potential difference on the resistor instead of the potential difference of the capacitor, that's actually going to still follow these exponential patterns, but the behaviors will be opposite. So if you think about the charging case, let's say that the EMF of the battery is 9 volts, just for the heck of it. If the potential difference on the capacitor is increasing, that means the potential difference of the resistor has to be decreasing at the same time. So if C is at like 2 volts, R must be at 7 volts, because they have to add up to make the EMF of the battery. So depending on which device you're looking at, you have to think about whether that particular voltage is going to be going up or going down. If the Q value of the capacitor is increasing, then its V is also increasing. But that doesn't mean that everything has an increasing V. And then the other thing you might have to think about is the current. What is going on with the current? Well, I already kind of answered that qualitatively. I told you that in the charging case, the current is really strong at the beginning because it's easy to put charge into the capacitor. And in the discharging case, the current is also very strong at the beginning because there's a lot of force pushing the charges out of the capacitor. So if you graph I as a function of time, it's going to follow the like decay pattern all the time. So that's the lower graph. You're never going to see the current in an RC circuit increase and level off to some permanent maximum value. The current has to decrease because eventually the capacitor is going to fill up and the current will stop. So, I think that's it. I think that's it for this first video. So I'm going to stop it, and I'll catch up with you in the next one.